Hello everyone, and welcome to the amazing video about L'Hopital's rule. I know students usually love this topic and they do really well with examples that involve L'Hopital's rule, so I'm pretty sure you will enjoy this video as well. We are going to start with the example when I will ask you to find the limit as x approaches 0 of sine x over x. We saw this limit before and many of you might jump out and say, I know the answer is 1. Well, how do you know? And did you ever check what is the proof that this limit gives you 1? There are several points of view on this, and when you see all kind of limits you don't really know what to do with them, there are several approaches. First of all, let's check why this limit is a troublemaker. When x approaches 0, the denominator approaches 0 and the numerator approaches 0, and the trick is we don't know which one is faster. Or maybe they have the same speed. But if x approaches 0 faster, then whatever is in the denominator shrinks to 0, much faster than at the top, so the result will be infinity, because dividing by something super small gives you a super huge result. If the numerator shrinks to 0 faster, then everything shrinks to 0 faster, and the answer will be 0. Well, there are several points of view how to start with problems like this. For example, you can do some numerical approaches. And, I just sat down at home and calculated what happens with sine at some kind of number which is close to 0. For example, 0.05. 0.05. What happens with sine at 0.03? And so on. Maybe even smaller than that. And the calculator told me that at 0.05 is going to be 0.04999792. At 0.03 is going to be 0.0299955. And then you compare the denominator, right? So you're checking what happens with x at those numbers. But when x is approaching 0.05, it's going to be 0.05 versus and 0.03 accordingly. Then you find those ratios and see where the ratios go. So if I'm dividing this number over 0.05, seems like they're almost the same. So the answer will be 1 or something close to 1. Same idea with the second case. Seems like it's getting closer to 1 and closer, so maybe we can make assumption that, the answer is 1. Well, this is not very practical. Are you going to be checking millions of numbers? And there's no way you can always check all of them. And how many is good enough to make a claim? So the second approach was graphical. And I showed this graph before when we were working with linear approximations. You can check that video. And this is the graph of y equals x and y equals sine x, green and the red. And then the idea was we're checking what's happening when x approaches 0 from both sides. And we kind of could, zoom in, increase as much as my computer allows me. And then see what's happening there around 0. And around 0, it seems like a green line and red curve, they basically become the same. I don't even see the red curve anymore, which kind of gives the idea that maybe instead of plugging numbers into the functions, I can plug numbers into the slopes of these functions. So I can find the slope of the line and the slope of the red curve, which is sine, and then compare those angles or find the ratio of those slopes of the tangent lines, right? So that was the idea of the graphical approach. So let me write down second idea is graphical. And the second idea, when we're actually using slopes of the tangent lines instead of the original functions, led to the definition of the L'Hopital's rule. Because what does it mean to find the slope of the tangent line? It means we actually differentiate, right? So L'Hopital offers this idea that every time you see case when you work with the limit of the ratio of two functions, it always only works with ratios. the ratio of the top and the function at the top and the function at the bottom. And when x approaches a, and a might be finite number, real number, infinite, maybe negative infinite, positive infinite, doesn't matter. And this ratio gives you 0 over 0 or infinity over infinity, plus or minus, doesn't matter. Then in this case, instead of comparing the ratio of the original functions, we can compare the ratio of their derivatives when x approaches this number. Basically, we're zooming in close to that number or infinity, zooming in so much that the smooth function, and how do I know it's smooth? Since it requires to have derivative, the function will be differentiable. And if it's differentiable, it doesn't have any cusps, and it also doesn't have any breaks, remember? So it's continuous. Then, if the functions are smooth, even if they're different, I can zoom in at the location I need it, and then instead of the original functions, I can consider slopes of the tangent line for each function, and then check the ratio of those slopes, which basically derivatives. That's a very good idea, and this idea was justified and proved with the name of L'Hopital's rule. Also, I want to point out, you see in my title there is no S, and in this picture there is S, because both are fine. People actually agree that both are correct. And L'Hopital himself, I think he was using the silent S, and then it somehow disappeared, and you will see notations in different books, both notations, which is fine. So let's try to use this idea we just had. This idea number 3. We're working with the limit sine x over x when x approaches 0. Before start using L'Hopital's rule, you have to justify that you can do that. To justify, you need to check that you have 0 over 0 or infinity over infinity case. Choose a different color to make nice notes. Sine at 0 getting close to 0 and x at 0 getting close to 0, so that it is a 0 over 0 case. The popular notation is to put LH together. Sometimes you will see slash, and some people even put it in a circle above the equal sign, and this makes a very good notation for people who will be reading your notes. They will know how come you jumped from original functions to their derivatives. They will see this little notation in red, and they will say, oh, this person used L'Hopital's rule, so this person differentiated each function separately. Make sure you have good habit to continue with good notes and good notations. At some point, you will become a part of the scientific community, and it's just very polite to make good notes if you expect other people to read your results or your work. L'Hopital rule tells me that instead of working with the function f over g, I can now work with the function f prime over g prime. Sine x is my f. Sine x is my f. So derivative of f will be cosine x. Then means cosine x goes to the top. Now, g function is x. So derivative of that function is 1. Then I will have cosine x over 1. You see, we don't use quotient rule here. L'Hopital rule tells me to look at the numerator and denominator separately. And now we have ratio of the derivatives instead of the ratio of the original functions. Let's check if this helped us to solve the limit. As x approaches 0, cosine of 0 is 1. And in the denominator, 1 doesn't go anywhere, it's still 1. So the answer is 1, and we knew that before. And this is how fast and convenient L'Hopital rule is, and it has a lot of applications. Let's work on more examples. Example number 2. How about the limit when x approaches 0, e to the x minus e to the minus x, all over 2 sine x. Interesting example. So we kind of know that exponential functions are very fast, but we know they are very fast at infinity. What is happening at 0 is a completely different story. And here, again, the function at the top, which is e to the x minus e to the minus x, competes with the function at the bottom, which is 2 sine x. As x approaches 0, whoever wins will give the result, or maybe the ratio will show you that they had the same speed, just like with the previous example. Since the answer was 1, it means sine x and x had the same speed around 0. That's what it means to have ratio 1. Let's check that we can use L'Hopital rule in this case. When I'm plugging in 0, I will have e to the 0, which is 1, minus e to the minus 0, which is still 1. That's 0. At the bottom, sine of 0 is 0. 0 times 2 is 0. So as you can see, we are working with 0 over 0 case again. And in this case, we can apply L'Hopital's rule. I will stick to the notation when I'm going to put L/H in a little circle. It just looks very nice. Some people just put LH, so you decide. Then, instead of working with original functions, I will just differentiate each function at the top and at the bottom of the fraction. E to the x gives me e to the x, minus e to the minus x gives me minus e to the minus x due to chain rule. Copy the function e to the minus x times the derivative of the exponent minus x, which is -1. Derivative of the function at the bottom gives me 2 cosine x. Now the limit becomes, as x approaches 0, I have e to the x plus e to the minus x, 2 cosine x. Let's check if this helped the situation. When I plug 0 now, what happens in the top? E to the x is still 1 and e to the minus x is still 1, but 1 plus 1 gives you 2. At the bottom, cosine of 0 is not 0. Cosine of 0 is 1 multiplied by 2 becomes 2. The answer is 1. Very nice example. And the ratio gave us, the result of the ratio is 1 again, so it seems like e to the x and minus e to the minus x and 2 sine x has the same speed around 0. Third example. Why we always work with examples 0 over 0? Let's have some kind of another example. For example, limit as x approaches infinity. And then we're going to work with, say, x squared and then e to the x. When x approaches infinity, x squared goes to infinity. When x approaches infinity, e to the x goes to infinity, so that's infinity over infinity case. Also, I want to remind you, plus or minus doesn't matter. So when you have different cases like this, it's still, L'Hopital rule still can be applied. So we're going to apply the L'Hopital's rule here. Before I do that, I want to remind you that in a different video called Speeds of Functions at Infinity, I actually explained you how to solve this limit faster. You know that e to the x is much faster than x squared at infinity, so the denominator will explode to infinity much faster in the long run than x squared. Since denominator explodes to infinity, dividing by infinity gives you 0, so we expect that e to the x wins in a denominator, and it's kind of a race here, functions are racing. Since denominator wins, the answer will be 0. But we can actually find this result using L'Hopital's rule. I will differentiate the top, it becomes 2x. And the bottom is still e to the x, because derivative of e to the x is e to the x. Let's check if this helped. When I plug infinity, or x approaches infinity, 2x still approaches infinity, and denominator did not even change, so it's still infinity over infinity case. But I can see that something changed. Instead of x squared, which was a quadratic function, now I'm working with 2x, which is a linear function. Every time I differentiate, the degree of the polynomial in the numerator decreases. So it seems like if I differentiate one more time, the function at the top becomes constant. Derivative of 2x is 2, and derivative of e to the x is still e to the x. Now, I don't need to use L'Hopital rule anymore, because I don't have infinity over infinity case anymore. 2 stays 2, as x approaches infinity, e to the x grows to infinity, so the answer is 0, just like we predicted. In this example, we use L'Hopital rules twice. Can you tell me what happens if I have x to the 5 in the top and e to the x at the bottom? How many times will I have to use L'Hopital rule if for the quadratic function I used L'Hopital rule twice? Then I will have to use it 5 times if I have work with x to the 5. And it's still going to work. One more example is going to explain you why L'Hopital rule actually makes sense and it works. Of course, in this video, I'm not going to provide the official proof of L'Hopital's rule. You can check it yourself. But I will give you some kind of intuition using a very nice, simple example with two quadratic functions. When x approaches 2, we're comparing what's happening around 2 with a parabola x squared minus 2x and with a parabola x squared plus 3x minus 10. Before we taught you L'Hopital's rule, do you remember how we used to work with these cases? The step 1 was, okay, check that everything is fine. Maybe you can just calculate the result. Well, when I plug 2 at the top, 2 squared becomes 4, minus 2 times 2, which is 4, the top is 0. At the bottom, I will have 4 plus 6 minus 10, that is 0 as well. So this is a case of 0 over 0 case again. And before we learned L'Hopital's rule, remember we actually simplified it. So before I knew that, it was probably the first exam of your Calculus 1 class. We ask you to factor out the function and the numerator becomes x minus 2 in the parentheses. Then simplify the function and the denominator. In this case, it will be x minus 2 and x plus 3. Then this bad part, and bad part in quotes, and basically a troublemaker cancels out. Then I will have x over x plus 3. I'm plugging 2 back in, and it will be 2 over 2 plus 3 is 5. That's what we did before knowing L'Hopital's rule. Now, using L'Hopital's rule, so this was one of the methods. Way 1. And I want to compare which way is faster. Way 2 is to use L'Hopital's rule since we have 0 over 0 case. I'll make a note, and you see how good to make notes like this. Now I know that the second way requires L'Hopital's rule, and now it will not be a surprise to a reader or even yourself when you read this example in a couple of months, why the top became 2x minus 2 and the bottom 2x plus 3. If you don't put a L'Hopital's rule notation, it's actually pretty confusing how come we jumped from the quadratic function to linears. But that's because I differentiated the top and the bottom separately. Now I can plug 2 in, and the result will be 2 times 2 is 4, 4 times minus 2 is 2, and at the bottom 2 times 2 is 4, 4 plus 3 is 7. It's supposed to be 7 or should be 5? Interesting. Oh, it should be 5 over here. I see. That was a typo. 5. That's how it becomes 7. So the answer is the same when you fix the mistake, of course. 2 over 7. And as you can see, L'Hopital's rule requires you basically one step. That's why students like it a lot. And you don't have to struggle with finding roots and so on. So why does this make sense? This makes sense because I want to show you why L'Hopital rule makes sense in general, not just for all kind of examples. If I go to the website, for example, GeoGebra, and I ask it to graph those two parabolas, this is what I see. So I graphed x squared minus 2x and x squared plus 3x minus 10. And this is the picture. Looks very nice. Two parabolas, one in green and one in blue. And I put a graph here for you. I made a screenshot. Here it is. Very nice screenshot. What I'm doing here, I will zoom in at 2 because x approaches 2. I will zoom in and I will zoom in, and I still see how curved they are. But the more I zoom in, the more it seems like at that particular location, those two functions look like a line. You see? How about this picture? Do you really see now that those two graphs used to be curved? They used to be quadratic functions. Now they look like lines. So if this is the case, can I, instead of working with parabolas in this case, can I work with tangent lines? I made a screenshot for the zooming in picture, and I will remind you that using both ideas of tangent of the equation of a tangent line and linear approximation, I can tell you that in each case, over here, very close to 2 when we zoomed in, I can say that the function f of x, any of the function, will be approximately a derivative of that function, and then x minus the point, in this case 2, right? So what I'm trying to say here is, instead of working with the limit when x approaches 2, and we're working with two parabolas, x squared minus 2x, all over x squared plus 3x minus 10, I can actually work with a limit when x approaches 2. When I zoomed in, I will approximate each function using linear approximation with the equation of a tangent line. Well, what is the equation of a tangent line for the top function? And that will be derivative of that top function f. If I say that f is the green function, and then I will use different color, say orange, and for the, let's do blue then. The blue function we'll call it g of x. That will be approximated by f prime x, x minus a. A here is 2. G prime of x. And then what is the common part here? That's going to be x minus 2, x minus 2. Why 2? Because x approaches 2. In general case, we just have x minus a and x minus a. So now look, this part is the same, so it can be cancelled out. And we end up to be working with limit as x approaches 2, f prime of x over g prime of x, instead of the limit of original functions, f of x and g of x. We're working with derivative of those functions. And then we know what derivative of those functions are, 2x. Limit as x approaches 2. X squared minus 2x was 2x minus 2 when you differentiate it, and x squared plus 3x minus 10 is 2x minus 3 when you differentiate it. Now you plug 2 in, and the result follows, which is 2 over 7. And that's kind of a vague proof of the idea and basically why L'Hopital rule works. Using graphical explanation here. Zoom in as much as you can and use linear approximation for each case. When you use linear approximation for each case, and then since we're working with ratio, I told you L'Hopital rules works only with ratios. When you find ratio of those functions, oh, that type should be g, the common piece cancels out, and then only the derivative stay, one in the numerator and the other one is in the denominator. And that's a cool idea of L'Hopital's rule. Hope you enjoyed the video. Keep working and you will do good.